In this video, we're going to look at logarithmic functions and their graphs. So what we're going to do is sketch a couple of graphs, f of x equals 3 to the x, and also what is going to be its inverse, you'll see, which is log base 3 of x on the same graph. Okay, so 3 to the x, this one's pretty straightforward. 3 to the minus 2 is 1 over 3 squared is a ninth. 3 to the minus 1 is a third. 3 to the 0 is 1. 3 and 3 squared is 9. Plotting those points looks about like this. Okay, so there is f of x equals 3 to the power of x. That's the exponential function. Now let's look at the logarithmic function. So let's start down here. Log base 3 of 9. Recall that means 3 to what power equals 9? 3 squared is 9. So log base 3 of 9 is 2. So we have the point 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2 right there. Okay, then log base 3 of 3 means this 3 to what power equals this 3? Of course, 1. 3 to the first is 1. So we have the point 3, comma 1. Log base 3 of 1. 3 to what power is 1? 3 to the 0 is 1, so it goes through 1, 0. All right, log base 3 of a third means 3 to what power equals 1/3, which is negative 1. So we have the point 1/3, comma negative 1 right about there. And then last one, log base 3 of a ninth. 3 to what power is a ninth? And that would be negative 2. I don't know why I wrote 3 there. Negative 2. Okay, so 1x is a ninth, y is negative 2. So this graph looks like this. And you can see how these are mirror images of each other over this line, y equals x. And they are inverses. So if we go look at all their x, y values, they're all reversed. So for right here, we have negative 2, comma 1/9. On its inverse function, we have a ninth, comma negative 2. Or negative 1, comma a third becomes a third, comma negative 1. These two functions are inverses of each other, which is why logarithmic and exponential functions kind of go together, and they mirror each other over that line. Okay, so y equals b to the x and y equals log base b of x are inverses. The domain of an exponential function, b to the x, is all real numbers. And its range is from 0 to infinity, and therefore in its inverse, these are flip-flopped. So the domain of log base b of x is 0 to infinity, the same as the range for b to the x. And the range for log base b of x is equal to the domain for b to the x, negative infinity to positive infinity. Now that one's not as obvious because it looks like it flattens out, but it never quite does. It slowly, right here, this slowly creeps up to infinity forever, very, very slowly. Okay, so this is what we just drew right here. If your base b is between 0 and 1, or they've got it called a right here, you would have this situation. This is the decaying exponential function, and its inverse would look like this. But that's it's pretty rare to deal with logs with a fraction between 0 and 1 for their base. So that's pretty much unheard of. Okay, here's a couple different logs graphed with different shapes. So log base 2 of x is the highest, and then they get a little bit flatter, and they hug this x-axis as the base gets bigger and bigger. Okay, for all of them, you can never plug in a negative number. The domain is 0 to infinity. Or 0. You can't take the log of 0 or a negative number, so that's the domain. And the range is always negative infinity to infinity. They never cross the y-axis, but they all have the same x-intercept at 1, 0. And that y-axis right here serves as a vertical asymptote. If the base a is greater than 1, then it looks like this. It's an increasing function, so f of x increases. And from this picture right here, you can see this logarithmic function. If the base was between 0 and 1, then the function would be decreasing. And all of these logarithmic functions go through 2 points. These are the two that I plot when I plot these. And that is 1, 0, and we can look at another easy point is when x is equal to the base. So if, for example, the base is 5, when x is 5, log base 5 of 5 is 1. So they all go through the point b comma 1, where b is your base. Okay. Okay, so the domain. You cannot take the log of a negative number or 0, so whatever you're taking the log of has to be strictly greater than 0. Okay, so whatever you're taking the log of, you say that has to be strictly greater than 0. So in this case, x would have to be strictly greater than negative 4. Otherwise, you'd end up taking the log of a negative number or 0. And it doesn't matter what the base is, you just take whatever you're taking the log of and set that strictly greater than 0 in order to find the domain. Okay, so let's take a look at this example. We're going to find several things for this one, starting with the domain. Okay, so for the domain, whatever you're taking the log of has to be greater than 0. So in this case, x minus 1 is greater than 0. So x has to be greater than 1. Any asymptotes? Well, one way to figure that out is to say that when you put a minus 1 right there next to the f, that x, that actually shifts the entire graph right 1 unit, which you probably know from transformations. So that's going to shift this vertical asymptote here right 1 unit. So it would actually be at x equals 1 instead of x equals 0. Okay, intercepts. Let's find the x and y. So the y-intercept is when x is 0. But actually that doesn't make sense since we can't plug in 0, right? We would get the natural log of negative 1. So there is no y-intercept. And x-intercepts occur when the function equals 0, when y is 0. So this is going to involve a little bit of solving here, which is something we've previously talked about. So I'm going to add the log to both sides to get the natural log of x minus 1 is equal to 2. And there's a couple ways you can do this. You can, students say e both sides, or you can convert it to exponential form. Remember, natural log means log base e, so this means e to the power of 2 equals x minus 1. So that's what I'm going to do. E squared equals x minus 1. So we're almost done. Just add 1 and we get x is e squared plus 1. Let's go ahead and get a decimal for that because we are going to graph this here. So I'm going to do e squared plus 1 to get 8.39 roughly. And that would be our x-intercept. Okay, so we can graph it, really also just using transformations we can graph it, but having the x-intercept is kind of nice. And then we'll determine the range. So I'm going to rewrite the function down here so we can see it. So what we are graphing is f of x equals 2 minus the natural log of x minus 1. Okay, I'm going to graph this using transformations. So the first thing you would do if you plug in an x is do the minus 1, so that's going to shift everything right 1. So I'm going to start by shifting the vertical asymptote right 1. And what I'm graphing first is the parent function, so let's do this one in blue. I'm going to graph y equals the natural log of x minus 1. I'll do the negative and the 2 next. So that's going to shift that point, which normally goes through 1, 0. Now it'll go through 2, 0. And then, let's see what else. The next one would be the base e comma 1. E is about, and here's what I'm referring to right here. Are these 2 points. B comma 1 is the other point it goes through. So E is about 2.7, but we've shifted it right 1, so this is going to go through 3.7 comma 1. That gives me at least one more point here. So 1, 2, 3.7 comma 1 is about right there. Okay, so it would look like that. Then next we've got this negative out front. So that, remember, if you have a negative out front, reverses all of your y values, so that flips it over the x-axis. That point would remain the same. This point would be mirrored down here. It would look like this. And then lastly we have this plus 2. So our final graph would be to shift all these points up 2. So this point goes here, this point actually it comes right back where it was right there. And then my x-intercept we had found was about 8.4, just a little bit off the graph, but 1, 2, 3, 4, 5, 6, 7, 8, be kind of right in there. And remember, it does keep going down forever. That's not an asymptote. There's no horizontal asymptotes here. Okay, so that would be my final graph there in red. And lastly, we're going to find the x-intercepts of this logarithmic function. Okay, and this is just a good algebraic practice. So finding x-intercepts means you set the y equal to 0 and we solve. So this is a good review of solving here. So when we set this equation equal to 0, we get this. And then to solve, we need to rewrite this in exponential form. So remember, we have an implied base of 10 there. So this means 10 to the power of 0 is equal to what's inside the log. And then we need to solve this equation. Well, 10 to the 0 is 1. So this is actually a quadratic equation. So I'm going to move the 1 to the right to get it equal to 0. And let's see if we can factor this. Be x plus 1 times x plus 3 works. So we get x equals -1 or 3 as the x-intercepts. Now this is a rather complex function which we would not be able to graph using transformations. It's just way too complex. But what we can do is check it by looking at a graph on a computer. So I'm going to pull that up here. Okay, now this is on Desmos.com. And here's the graph. And you can see we have an intercept there at -1 and at -3. Oops, which, yeah, I just left off a negative there. So yeah, -1 and -3 are our x-intercepts. And that's all we have for logarithmic functions.